Thanks for the introduction, Matt. Yeah, so today I'm excited to talk about some of my research from my doctoral studies at Queen's University. And today we're going to focus on measuring differential soil settlements using distributed fiber optic sensing along buried infrastructure. So monitoring ground deformation is essential for the safe operation of urban construction activities, as well as the safe operation of infrastructure. And today we're going to focus on this case on the left, where we're looking at a buried pipeline being exposed to differential settlements associated with the formation of an underlying normal fault. However, the results are kind of also applicable to other settlement profiles, whether that's a settlement trough here on the right imposed by the installation of a new tunnel under a pipeline. And we can also extend these results to kind of other infrastructure scenarios. Maybe you want to monitor ground deformation along an embankment. But there's lots of different conventional approaches to measuring these ground deformations. But one newer approach for monitoring subsurface ground deformation is fiber optics, which offer potential improvements to both sensing length as well as the spatial resolution of our measurements. So in this study, we use this apparatus at the Queen's University Geoengineering Lab, which we refer to as the split box. And essentially, it has a stationary footwall section and a moving floor hanging wall section, where we can operate these screw jacks to lower that moving floor and simulate differential settlements associated with the formation of a normal fault. So typically, in one of these experiments, we'll have a buried test pipe, and we'll use fiber optics bonded to that test pipe to monitor its strain response. However, in this experiment, we included these buried fiber optic cables adjacent to our pipes to try to test their performance for detecting the fault, as well as measuring its fault offset or the form profile of the soil. So a little bit more overview on the split box before we go into the results. On the left here, we have an image of our split box before backfill, and we can see the stationary footwall side on the far end, and then our moving floor hanging wall section on the close end. In the middle here, we have a typical test pipe instrumented with fiber optic cables before backfill. And then on the right, we have our final surface elevation before applying our fault offset. And then after our test, we get the form profile at the surface, where you can see the settlement that's been imposed. Transitioning to the current experiment that we're going to focus on today, this experiment included 2 test pipes highlighted here that were instrumented with fiber optic cables and were part of a larger study to investigate the response of buried pipes with and without axial restraint. And then on the right, we included these 5 fiber optic cables, which we selected to represent a range of cables that may already be buried beside a pipeline or may be installed to monitor or detect ground deformation. The first of these cables was a multi-core cable here, showing you can see that there's a number of internal cables inside that are inside of this smooth exterior jacket. The second cable we included was a ribbed 1 cable, which has this strain-locked internal fiber that's bonded to this ribbed outer core, which gives it greater compliance with the adjacent backfill soil. Our third sensor we included was a temperature cable, where we have these 2 fibers that are loose inside this steel tube, which essentially allows them to be sensitive to temperature changes, but be insensitive to strain imposed by movement of that cable. And then the last 2 cables we included were 2 other ribbed varieties, where we have embedded fiber optic cables inside this epoxy fiber matrix. So we saw some potential limitations with using these fibers, the main one being that with a single fiber, you can't estimate curvature of that fiber, and without curvature, you can't estimate its deformed shape without making some kind of mathematical assumptions. So that led us to coming up with this strip here in red, shown in the which we're going to refer to as the strip sensor. And essentially, this is a thin piece of low-density polyethylene plastic with fiber optic cables bonded to its upper and lower surfaces, which enable us to measure the curvature of that sensor and then infer its deformed shape as well as the deformed shape of the surrounding backfill. So with that in mind, we wanted to be able to compare the deformed profile of our strip sensor to the deformed profile of the soil, So we use this window on the side of the facility where we can take pictures of the soil throughout the test and essentially measure the displacement of the soil using digital image correlation. The first piece of data that we're going to look at is the strain response along our buried cables, where we're going to show strain versus distance from the fault along 4 of our cables, shown here on the left. And in this slide, we've excluded the temperature cable. We didn't measure any meaningful strain along it because those internal fibers are loose and aren't sensitive to strains imposed by ground deformation. And then on the right, we're showing our displacement field of the soil obtained through digital image correlation, where we're highlighting the elevation of our sensors and the location of our fault. So you can see here at a fault offset of 20 millimeters, we have a very subtle deformed profile. However, we're already starting to measure some strain along our fiber optic cables at the location of the fault. When we increase our fault offset to 60 millimeters, we're getting a more abrupt profile and an increase in strain at the location of the fault. And then finally increasing to 140 millimeters. Now we have this more well-defined shear band in the soil, which results in a more distinct peak along our rib 1 and rib 2 cables, showing some promise for using those cables to detect soil deformation. However, along our multi-core cable, we have a more distributed strain profile that kind of hints towards it being better suited towards other applications other than monitoring ground deformation. And then along our rib 3 cable, which was our stiffest cable, we didn't develop a lot of strain along it, and it's potentially better suited towards applications requiring greater survivability or needing to accommodate larger ground movements. So with these strain profiles, some other researchers have been interested in trying to use those strains to estimate fault offset. So in this slide, we're showing the actual fault offset we imposed versus the approximate fault offset that we calculated using the using the analytical method proposed by Chen and Yi 2025. And essentially, this analytical method depends on 3 parameters. The first being unanchored length of the fiber. The second is the average strain measured along the fiber. And then the third is I-soil, which is a deformation length scale parameter and essentially describes how long that deformed soil profile is. So our first 2 parameters we can measure with our fiber optic cable, and then this third parameter you need to know about your system. Lucky enough for us, we have a previous researcher that has defined I-soil for our apparatus and our soil-like conditions, and if we use that parameter with our results, we get a reasonable estimate of fault offset, where this solid black line represents a 1-to-1 correlation. However, if we use a smaller I-soil value, which was proposed by the researchers that came up with this analytical tool, you can see that the shorter parameter, which represents a nearly vertical fault scarp, significantly underestimates our fault offset that's been imposed. And this highlights that this analytical tool is sensitive to this I-soil parameter, which depends on your soil conditions and potentially limits its, since this parameter is difficult to estimate, it limits its applicability in field scenarios. So with that in mind, we were trying to develop a tool to more directly measure soil deformation. And the tool we came up with is this strip sensor. And on the left here, we have axial strain along that strip sensor, which essentially develops in a similar manner as strain along the buried fiber optic cables. However, the additional piece of information we get with the strip sensor is curvature, which is shown here for 20 millimeters of fault offset. And you can see that we get this double curvature profile that is localized at the location of the fault. As we increase fault offset, you can see that curvature increases, but still remains localized at the fault. Using these 2 pieces of data, we can approximate our strip sensor's deformed shape, which we can then use to infer the deformed soil profile, which we're showing here on the left, where the blue line is the approximate deformed shape of our strip sensor, and then the green line is our soil displacement profile at the elevation of the strip sensor. So at 20 millimeters of fault offset, you can see that the 2 profiles agree well, and then as we increase fault offset, you can see that generally remains true with some divergence in results at 140 millimeters of fault offset. However, in this hanging wall region, The two results remain within about 5% of one another, which seems reasonable for practical applications. And then additionally, we did a survey of our strip sensor after the test. And you can see that it generally followed the path of the soil. It shows that our strip sensor was flexible enough to follow the soil for this scenario. Then finally, we have this, since we had our fiber optic instrumentation buried adjacent to a test pipe that was also instrumented with fiber optic cables, we can compare the strain along those cables to that of the test pipe. And you can see a lot of variance in results. But essentially what we're seeing here is that these ripped cables aren't measuring the strain of the pipe because they're not bonded to the pipe. They're being subjected to different strains because of their relative stiffness to the soil. And then again, if we look at the curvature of our strip sensor in comparison to the curvature of the pipe, you can see that the strip has much greater curvature and is much more localized at the fault because it's much more flexible. So again, kind of these cables, while we can use them to detect the formation of a fault or even make it or potentially measure the form soil profile, we can't directly interpret the pipeline integrity without going into using like a finite element analysis with our inferred soil profiles. So in conclusion, we conducted this kind of large-scale test where we buried these fiber optic cables and subjected them to differential sediments associated with the formation of a normal fault. And we saw that the buried fiber optic cables can be used to detect the location of normal faults. However, not all of these fiber optic cables are equivalent. And these buried cables do not directly measure the pipe strain. Secondly, we saw that we can use analytical methods to estimate settlement from measured strains along these cables. However, it really requires precise knowledge of the soil conditions and the ground deformation mechanism. And then finally, we introduced the strip sensor as a promising tool for more directly measuring differential settlement profiles, which could be extended to monitoring lateral deformations or even 3D ground deformations. Thank you for listening, and I'd be happy to answer any questions. And then feel free to reach out to either myself or Brad if you have other questions to ask. Thank you.
Hey, Jonathan, looks like we got one question in the chat here. I'll read it out. The strip sensor seems like a really interesting approach for pipe strain. Does the sensor still require an interrogator to measure these strains? And then there's more questions there, but I don't think we have time to answer all of them, but I think you can follow up with Heather afterwards.